Good morning, and thank you for joining us for this live talk with our amazing STEM ambassador, Mark. To celebrate tomorrow's Engineers Week, Mark will talk about his 20-year journey in aerospace engineering. He'll share what an aerospace engineer does, how he built his career, and why the motto, fail fast, learn quickly matters, showing that mistakes are part of progress as long as you learn and keep going. Feel free to pop your questions in the chat and Mark will answer as many as he can at the end of his talk. So let's get on with the talk. It's over to you, Mark. Good morning.
Good morning, everybody. It's a pleasure to talk to you today during tomorrow's Engineers Week. And as Lisa said, I'm going to talk to you about my career in aerospace engineering. So, why am I doing it? Well, the theme of tomorrow's Engineers Week is Dare to Discover, and to show that it's okay to not get things right the first time, and trial and error is at the heart of engineering and technology, and that is certainly true of my career today. All of the job roles that I've done so far that I will go into have got or have had a lot of elements of trial and error in them, and I will take you through a few of those examples and show you why it's okay to not get things right the first time, so long as you learn quickly. So, yeah, the presentation will include what do we mean by aerospace engineer, what I've done so far, and as I said, some examples from my career so far, and of course some time for you to ask some questions at the end. I will caveat this by saying that this presentation is only, of course, my experience. I can only tell you what I've done so far. I'm sure you've heard from other engineers that've got lots of different stories. So, as a bit of background, as to why this is important. So as of last year, about almost a fifth of all jobs in the UK employed people in engineering, but that's set to rise. The problem is that there is already a skill shortage. There's not enough people going into the engineering sector, and so that's why events like tomorrow's Engineers Week are so important, to hopefully to try and inspire some of you to pursue a career in engineering, because, well, in short, we need you. We need more people. So what do I mean by aerospace engineer? People ask me, what do you do? And I say I'm an aerospace engineer, and they look at me rather blankly. So in short, aero means I work on the design and the design and construction and development of aircraft, and space means we're working on the design and development of spacecraft. That's essentially what it means. The role is very varied. There's lots of different careers with lots of different companies and take you down lots of different routes. But essentially, it's the design and development of aircraft and spacecraft. Why did I choose a career in engineering? So, well, ever since I was probably old enough to know what an aeroplane was, I was interested in them. I have always had a love of science and engineering, and I enjoy the practical hands-on work. I enjoy getting in a workshop, getting my hands dirty, as well as all of the theory side. And as an engineer, there's a lot of the theory side. I've spent almost 20 years in engineering so far. Still learning, still got lots to learn. And I was a kid that loved taking things apart, putting things back together. Normally better at taking things apart than putting them back together again. And building stuff out of Lego and Meccano and all sorts. I had that Lego set that I've got a picture of there. So that's what I was like as a kid, and that's that love of science and engineering has taken me all the way through to the other picture, which is me stood in front of a World War II Spitfire aircraft shortly before I actually got to go in and have a flight in it. So how did what's my path been to date? So when I was in school, of course, I did my GCSEs and then followed that up with A levels, and then I went off to study aerospace engineering at university. You know, when I left school, there weren't the options available to students as there are today. It was either really university or get a job, whereas now there's lots of apprenticeship options. There's degree apprenticeships available. But for me, it was the university route. And a brief summary of some of the jobs that I've done since leaving uni. So to begin with, I was a technical author, which essentially means that I wrote lots of instructions for taking things on and off aeroplanes, or for testing things that were attached to aeroplanes. Sometimes I actually got to get hands on with the aeroplanes themselves and put what I'd written into practice. That was a great way to build on the knowledge foundation that I gained at university, and start building up my my real world experience. And then the vast majority of my career to date has been spent as a research engineer, and this is what I'm primarily going to focus on for the rest of for the rest of this presentation, is taking you through a few examples of what it's like to work in research and development, and why it's important to realise that things aren't going to go right the first time, and that if you're not making mistakes, you're really not doing the job properly, because you're not testing all of the potential avenues available to solving a problem. And I spent a lot of time working on current and future technologies for airliners. And now I'm a data analyst. I've been a data analyst for a few years. It's a bit of a different discipline, but my job is to provide independent and unbiased, that's the important part, independent and unbiased evidence to support my customers' decision making. So they will have an idea in their head of what they want. My job is to do some independent analysis to find out if what they think they want is actually what they want, and then present them with evidence that hasn't got any of the bias behind it that they've got in their brains. So let's get on to some examples. In my final year of university, I did a group project. There was about 12 of us in a group, and our job was to, our objective was to design, build and fly 2 large remote control aircraft in the space of 1 year. So that was a tall order. So the first aircraft on the left there, so this is a screen grab I've taken, well, a couple of screen grabs I've taken from a video, so apologies for the poor quality. But that first aircraft, we took an aircraft that had been built by another team the previous year, so we kept the main body of the aircraft, we kept the tail at the back of the aircraft, but we were told to design some new wings. So our lecturers had ideas in their head of what they thought a new wing could look like, and we were told to take those ideas, test them to see if they worked. And on the picture on the right hand side, you can see there is an inherent problem, because during its flight, there's most of the aircraft, but one of the wings has made a bid for freedom. It snapped off. And the aircraft crashed and broke into hundreds of pieces, and we had to go and recover them all, put them in a couple of plastic bags, take them back to the university and figure out what went wrong. And we learned lots of lessons from that, that we could then take forward to build our second aircraft. So this one obviously looks completely different. We were able to go back to our lecturers after that first aircraft crashed and said, actually, some of the ideas that you thought were worth testing haven't worked. That was just as important as figuring out what did work as figuring out what didn't work. And then we applied those to the design of a completely new, and I have to say, much slicker looking aeroplane that conducted a completely successful flight. It was exceptionally windy. It was tough conditions to fly an aircraft in. But yeah, it took off fine, it flew fine, and yeah, on the right there is the point where everybody breathed a sigh of relief when it had landed and come to a stop, and we didn't have to sweep it up and put it into plastic bags. As I said, I've spent most of my career to date working as a research engineer. So as a bit of background before I go into some of the examples, aircraft designers are always looking for ways to make aircraft lighter, so they burn less fuel, ways to make them cheaper and repair them cheaper, and ways to make and repair them faster to get them off the production line and into service as quickly as possible. So the company I worked for, we looked at researching and developing ways to make aircraft parts out of a wonderful material called carbon fiber. Now, carbon fiber is a fantastic material because it is much lighter than metal, which is what aircraft are traditionally made from. But carbon is also very, very strong. So yeah, we can address bullet points. Well, definitely bullet point 1, and then we were looking at ways to address bullet points 2 and 3 as well. Now, as that picture shows, a carbon fiber part, it's not just a solid part like a piece of metal is. It's made up of often hundreds of different layers, and each one of those layers is less than a millimeter thick. So you know, less about the width of a fingernail, sometimes even less than that. So, as I said, rarely does a new idea work first time, and it often needs testing many times. But before you find something that actually works, before you find a good solution. And I'm going to go through just a few of the many examples that I have that illustrates that point. So here's typical aeroplane. Did a little bit of work on the Airbus A350, but I'm not saying that's all I worked on. This is just to illustrate some of the areas of a general airliner that I worked on. And the company that I worked for specialised in building wings and building engines. So if we take the top left example here, looking at the end of a wing. So if we want to test a new idea, and we were looking at ways to make this particular part of a wing a lot differently to how it had been made before, not just out of carbon, but the way we designed the structure of the piece of wing to try and take as much weight out of it as possible. But we were testing something entirely new. So the way to do that is not to go and build a full-size piece and then test it to destruction to see if it works or not, because if it doesn't, that's a really expensive way of doing things, and also a very time-consuming way of doing things. So what we do is we make lots of small test pieces that are representative of different parts of that wing structure. And by making lots of different test pieces, we can get through a test program a lot faster. We can test lots of different ideas. So this particular example on the left-hand side there, I once made about 300 of those for a test program, and a test program that lasted, I'd say, at least 6 months from memory, possibly even a bit longer. So what we do is we make our little test pieces, and what we've done here is we've deliberately damaged it. We had a little device where we basically just dropped a weight into the middle of the test piece and put a hole in it. That was great fun doing that. And then we put it on another machine and we pull it apart and test it to destruction to see just how strong it was and how strong it would be if it was damaged in service. And eventually we hit upon a design that worked well, gave us what we wanted. And then it was time to build the full-size piece on the right-hand side there. So you scale something up from a tiny little test piece up to a huge piece of wing, but with the knowledge and the evidence behind you that you know you're not wasting lots of material, lots of time and money building a full-size piece, because chances are there's a very high chance it's going to work. That, of course, will then go off to be be tested as a full-size piece and tested to destruction. But it means we only have to test it to destruction once instead of many times. Another example was, as I said earlier on, piece of carbon fiber is built up of many layers. So if, I don't know, a piece of debris off a runway or a bird hits the aircraft, the damage can often occur. It's often not visible on the surface of the product. It's the damage often occurs many layers down. And ordinarily, when parts are repaired after they've been damaged, it would be a person with a sander who would spend hours and hours and hours grinding away down through the various layers of a part. It's very messy. It's very time consuming, quite expensive, and the results can sometimes not be as clean as we would like. So we investigated a way of using a laser. So this was a 2-year program. So it took 2 years to try and test various ways of setting up a laser so that we could produce a nice clean repair that you see on the right hand side there. And each of those rings that you see is one individual layer of carbon, less than a millimeter thick. So yeah, we spent 2 years testing various combinations of parameters of the laser, of the material, how best to set the part up under the laser. Yeah, we tested lots and lots of different things, and that was a result of it not working the first time. You don't test one set of parameters and that's the sudden result. You have to test. Well, we tested hundreds and hundreds of different parameters until we set upon something that worked. My last example is I spent some time developing, helping to develop the next generation of jet engine for an airliner as well, and this followed the same principle. I worked on the piece that sits around the big fan at the front, the circular piece at the front of the engine, so that if one of those fan blades did break off, it wasn't going to bust through the engine and cause untold damage to the rest of the aircraft. Now, traditionally, the fan case, as it's called, is made of metal, but to take weight out of the engine, we looked at ways of making it out of carbon fibre and using robots to make the part instead of relying on people to do it, because we needed a fast, repeatable process that can knock out fan cases at a large rate of knots. So it was the same principle, really. It wasn't just a case of getting those robots in, plugging them in, turning them on, programming them with one set of parameters. Off it goes, and it all works the first time. No, again, years and years and years were spent trying to perfect the method to something that gave the right balance of a reduction in weight, but also making sure it was a process that could be repeated time and time again. And as with the previous test program I talked about, we made lots of small-scale trial parts on the left-hand side there, so we weren't wasting time making enormous full-size pieces. But once we got once we were sure we had a process that worked, we'd make some full-size pieces in the middle there, and then eventually, once they'd been tested and refined, it went on to the full-size, all singing, all dancing engine that you see on the right-hand side there. So that is just a very quick run through in 20 minutes of just some of the reasons why it's important to remember that you're not always going to get things right the first time. Trial and error is a huge part of working in engineering, and making mistakes, so long as you learn from them quickly and apply what you've learned, is all part of the job. It's nothing to be afraid of. So yeah, I think we've covered all of those bullet points there. I've told you what Aerospace Engineer means. Quick whiz through my career in engineering so far, and yeah, giving you some examples that have hopefully been interesting, and that you'll keep in mind going forward. So now time for the all important questions.
No, thank you very much, Mark. That was truly insightful, and I wrote down here that the 3 Ps here, that I think you've got to be persistent, patient, and very good at problem solving. So yeah, well done. Well, we've got some great questions that have come through, so I will run through those with you now. This one here is, what kinds of things do aerospace engineers design or work on?
Well, as I said near the start, it's so aerospace engineering as a discipline is all about working on the design of aircraft and spacecraft. Now, the companies that I've worked for so far are specialised in designing wings and engines, because that's what we're really good at in the UK. But there's companies that specialise in designing the main bodies of aircraft, the tail at the back, the wheels, every single part, every single nut, bolt, and part of an aircraft has got to be designed somewhere, and all of that comes under the umbrella of aerospace engineering. You can be you could specialize in aerodynamics, so what makes a wing particularly good, how to design a wing to give you the best and most fuel efficient flight. You can be a structures engineer, so you can actually work on the structures themselves, kind of like I have, and work out what designs are likely to give you the strength and the weight that you want. There's there's all sorts of disciplines. Too many for me to go into in the next 10 minutes.
Great, thank you very much for that. Question here is, how is new technology changing the aerospace industry?
Oh, that's a great question. So it's not just aerospace engineering, it'd be engineering in general, but it's a fast-moving, fast-paced environment. Something that I found to date is you could be working on a project for a year, not even get to the end of it, and somebody will say, you know what, this isn't relevant anymore because a new technology's come in that we need to investigate. So we're going to put this project back on the shelf and we're going to start something entirely new. Automation is a big thing, using robots. Just one of the examples. I went through making engine parts, but robots, they don't replace people. The people just have to learn to do new things, but robots can make something time and time again that looks exactly the same, whereas with people making it, there's always going to be some little differences from one part to the next. So the use of robotics is a huge part coming into engineering. AI as well. AI seems to be everywhere at the moment. It's a blanket term that means lots of different things to lots of different people. But within engineering, or particularly within data analysis that I currently work on, there are the machines, robots will produce vast quantities of data that one person on their own can't possibly deal with. So potential uses for AI will be to help to go through all of that data and pick out all of the relevant stuff. Then, as data analysts can look at in far more detail. In aerospace engineering, aircraft, airliners that fly around the world nowadays are constantly transmitting data back to the manufacturers about how every single part of the aircraft is performing. That's a truckload of data for an analyst to try and work their way through. So that's where AI has potential for lending a hand.
Yeah, it's funny that you've mentioned obviously automation and AI. We did have a question here from somebody that said, do you feel that AI will reduce the need to sort of fail quickly, or does it take the fun out of engineering? Does it take the fun out of your role, having robots doing some of your job for you?
The AI part I can't really speak of because it's only just starting to rear its head, so I haven't got the experience of that to be able to give you some examples. But yeah, the project I talked about where we were using a laser to try and repair an aircraft part, I did spend many hours just sat next to the machine while it was spinning round and round doing its part, and I was just there to keep an eye on it and then reprogram it at different times. There were times that could get quite tedious, yeah, and sometimes it does take the fun out of it, but that has to be balanced against the advantages that it offers to the industry and to the customers as well.
Yeah, I totally understand that. Question here is, are you finding that there are many females working in the aerospace industry? Are more coming through?
Right, so as I've got the slide still available, that answers one of my pre-prepared questions, just in case there weren't that many. So are there many women in engineering and data analysis? So from my personal experience, I currently work in a team of about 18 people, of which there are 5, so about a quarter. But where I work, I'd estimate there's about a 50-50 split between men and women. A survey conducted by in 2023 concluded that only about 1 in 6 girls saw engineering as a potential career path, and 1 in 6 of the engineering workforce at that time were women. But there are initiatives such as International Women in Engineering Day in June that aim to encourage more women to go into career in engineering. And yeah, it's something that's open for everybody. Yes, what stereotypes that may have been there in the past just do not apply. There's lots and lots of different career paths available within engineering, and we need all sorts of people to be able to fill them. We need people that think differently, because that's the way we make progress.
No, that's really good to hear, and obviously inspiring for the female visitors today. So thank you. Let's move on. We've got a couple of sort of personal questions here. This is from Year 8, Cannons High. What is your most fond memory throughout your career to date?
That's a great question. That's a really good question. I have been lucky enough to work on some really interesting really interesting projects, and I think my fondest memories are those where I get to see the things that I've worked on in a laboratory actually make it onto an aeroplane or onto another platform. Actually get to see them fly, get to see them go into service. And yeah, I have some other good memories as part of my previous job. I got to spend a few days in Paris, paid for by the company, going to a trade show. That was good fun. We made the most of that. And probably my fondest memory in general, not just in my career as an engineer, but my love of aviation so far, is getting to fly the World War II Spitfire 7 years ago. There is nothing that is going to beat that.
Yeah, great. Lovely, something to talk to your friends and everything about. Yeah. We've got a question here from Sirius Academy, North 8R4. I know you've mentioned that obviously some things you're working on, you can get to a certain point and then it's taken back and you start all over again. But I think it's just as a general sort of idea for people is, how long does it actually take to build an airplane?
So the way it works is that an aeroplane itself, not all of the parts are built in one place, particularly something like an airliner. So as I said, in the UK, we're really good at making engines and we're really good at making wings. So there's big factories in the UK that will just be constantly churning out those parts. And depending on the size of the part, it could take days, it could take weeks just to make one part. And then those will be shipped off to somewhere. Well, there's an airfield near Chester called Broughton, It's where the big one of the big Airbus factories are. So all the parts are shipped up there and they're put on aircraft and they're flown out to Toulouse in France, where they are taken to an enormous factory that actually put all the aircraft together. It's like putting together pieces of a jigsaw. So the wings and the engines from the UK will be taken to Toulouse and they'll be joined up with the body of the aircraft that's made somewhere else, the tail of the aircraft that's made somewhere else in the world, the wheels that are made somewhere else. You get parts from lots of different countries that have all got to come together, put together as an enormous and very complicated jigsaw, but before it's then put out the door and flown off to a customer. So it takes a long time to build one aircraft, but there's always a production line going. So there's always, as one aircraft is just starting, there's another one that's about to roll out the door and be delivered to a customer, and there's just that continuous line. So there's never a let up in producing the product for the customer.
Okay, well, Mark, we're running out of time, but if we can get just a couple of really quick answers for you, we can try and get a couple more questions in. So one quick question from James is, how many products or craft or parts would you say that you have developed over your time?
Oh, crikey. I'd probably say it's in the tens. It's definitely not in the hundreds, because in research, a research program can take a couple of years, but it's probably in the tens. I couldn't put a number on that.
No, that's good to hear. And what subject at school would support an application to obviously go on and then study aerospace? So that could be people that even starting from the GCSEs to A levels. What would you say are the other good examples to study?
Okay, so yeah, I've got another one for that. So when I was at school, I needed 3 A levels to go off to university, and to be an engineer, maths and physics are a given. They are the most important ones, and then whatever other subjects you choose to study alongside that is more your choice. So I chose geography and history because those were the ones that more they felt a bit different, and definitely a bit lighter than studying maths and physics. But of course, university entry requirements probably changed since I was there. So I would advise, if you're thinking of going off to uni in particular, or you want to do an apprenticeship, have a look and see what they will require. But I can guarantee maths and physics will be in there.
That's great. Thank you very much for that, Mark. And I think one final question to end this on is, do you have a favourite aircraft? And that's from Year 8, Cannons High School.
Oh, I've mentioned it a couple of times already. It has to be the Spitfire. It's the greatest of all time. Yeah, and I've written about them. I've built them, and I've flown them. So yeah, for me, it has been and always will be the Spitfire.
No, thank you very much. So that wraps up the call today. So thank you very much. Thank you everyone for joining us today. Thanks to Mark. We hope it's given you an new insight into the world of aerospace engineering, and we wish you every success as you explore your future career paths. So thank you everyone. Goodbye.